So a long time ago, not quite in a galaxy far, far away, I might feel that way sometimes, uh, a, um, a mathematician by the name of G. Spencer Brown put forward a little book called The Laws of Form. And it's written in such a way that, people couldn't make heads or tails of it. They weren't sure if it made any sense or not, especially as he got towards some of the other results in the book. People didn't think it was meaningful. It sounded like noise. And this is compounded, I think, because Spencer Brown made some erroneous claims about four-coloring, if memory serves. I might have that wrong, but I know that he made some claims that were later discovered to be erroneous. But of course, it's hard to avoid that if you're a practicing mathematician. Anyway, some years after that, Francesco Varela and Luke Hoffman proposed a model of his arithmetic and algebra, of Spencer Brown's arithmetic and algebra, and put it on firmer footing. And then more recently, I was reading Sharp's book on differential geometry, and on his second fundamental form, I hit a problem because there's a type mismatch in one of the equations. And so I was looking for, some additional materials by him that might resolve the type mismatch. And I discovered that he had also developed a model of G. Spencer Brown's laws of form. And I read the paper, and it turns out to be quite understandable. He develops it in terms of nested planar regions, and then builds a graph of the nesting. He builds a graph that reflects the nesting structure. And it perfectly verifies. It's a full and faithful model of the laws. So I thought about it, and I said, well, is there a syntactic presentation? And I realized that S expressions, in fact, provide a full, faithful version of the graph that Sharp presents. So without further ado, essentially the grammar that generates the expressions of the laws of form, Spencer Brown typically denotes dot with just blank space, which is part of what makes it so difficult to understand. But an expression E is either the empty expression, or it's an expression that has been crossed. So this is the notation he uses for crossing. Or you have essentially a kind of multiplication, which is placing expressions side by side. And then Spencer Brown's convention is to write this as this, right? So we infer the dot. And then he has a couple of, and so you can see that this generates a wide variety of expressions, right? In particular, you can have like, a cross next to a cross, and then you can have a cross over that, and then you can have a cross next to that. Hopefully that's making sense. People can kind of visualize that. Does that make sense to folks?
Yeah, makes
cool.
sense.
So then the rewrite rules are, if you have two crosses like this, now remember, that's really these things. If they're next to each other, then that reduces to just a single cross. And if you double crossings like this, then that goes to just the dot. So you have a dot here, a cross, and then you cross again. So he uses very colorful language. To cross and cross again is not to cross. So that removes this pair, and it turns out that you can get that every expression reduces to either the dot or the cross dot. And that's there's more. He introduces some other equations and gets another algebra which delivers a canonical form. It gets a quotient algebra which delivers a canonical form, and we can do all of that too. But the main idea here is just so if you look at Sharp's paper, what you'll discover is that he roots all the graphs are rooted. So I've denoted the root with a different kind of parenthesis than the normal parens. But in general, we can provide interpretation. So the bold brackets are our interpretation function. So the interpretation of the dot is just the bold brackets. If to interpret a crossed expression, what we do is we interpret the uncrossed expression, and then if this thing were the dot, then we just put the parens around the empty parens, right? And if it's not the dot, meaning that there's actually something there, then we can just put parens around that, right? So crossing is basically nesting in parens. And then placing things side by side is literally just placing two expressions side by side. So you interpret both of these in parallel as you wish. If they're the empty, then it's just the empty. If either one of them is empty, then it's just the other one. And if they're both there, then you place them side by side. And again, if memory serves, I believe that Sharp nests them below one pair of parens. That may not be the case, and it doesn't matter. You can just remove these, but that's essentially that's the idea, right? So clearly, you can just intuitively see that we have a full and faithful translation, and so in particular, the rewrite rules will translate as well. But now we can see, because we have a syntactic expression, like not a sort of semi-geometric expression or a geometric expression. We can see that we need to place these within a context. So it's really K of these two things reduces to K of that thing, or K of this thing reduces to K of that thing. And again, you'll get that all expressions reduce to one of the two values. So hopefully that's clear. Do people understand the basic the basic translation?
Greg, could you check the waiting room for Raphael?
Oh, sure, no problem. All right, so Raphael's in. So do people? Hi there. Thanks for joining. So do people understand the basic translation?
Yes, makes sense.
Cool. All right. So then the next layer of complexity in the laws of form is that he adds variables. So
can you share the screen, please?
Yes, of course. All right. So he adds variables. So in modern day language, right, in BNF form, all we're doing is adding one more base case. And then he adopts some conventions that if you have two variables side by side, that's really variable multiplication. And so in my world, and if you were to ask a compiler to, or a parser to interpret this grammar, a parser generator to interpret this grammar, well, the first thing it's going to want to do is to say, well, how do I lex these variable things, right? Where do these variables come from? Tell me what they are, right? And this is in some sense the essence of the question that the row calculus asks, right? Where do your variables come from? And if they come from something outside of your system, well, that is a source of sneaking in extra structure. So that question, if you leave it open, if you say, well, I don't care, you hand me a set of variables, that means that you're turning E into a monad. And where E takes, for example, it could be a monad on set, it could be a monad on other things, but let's use set as our example. If you know, we take the category of sets and functions, then the monad takes a set X to the language generated by the grammar where X's, the little X's are drawn from the big X. Is that clear? People understand what I'm saying?
Yes. This is like a E is parameterized by.
E is a parametric type constructor. That's right.
Yes.
Okay, so now let's consider a fixed point. So I'm going to apply, I'm going to build this operator that, given these monads, monads like E, when you apply R to E and then you apply the resulting thing to X, you get E of what you started with. So that's a recursive equation and it has a fixed point. And you can realize this. You can realize this in a couple of different ways. Like, you know, if you try to write that down in Haskell, there are a couple of different things you can do. If you write it down in Scala, there are a couple of different things you can do. But one way to think about it is adding this production here. X's are E's, but they have an extra decoration to denote that they're X's. Look familiar?
Oh yeah.
Right. So the point is that the row trick is actually quite generic, right? It's not specific to concurrency. It's an operation. It's a general operation that you can apply to monads. And in fact, it, as I've mentioned before, the general form operates like a derivative. So it's lowering the rank. So if you had a 2 monad, it would drop it down to a 1 monad, and a 1 monad, it drops it down to an object in the category. If you have a 3 monad, it drops it down to a 2 monad, and so on and so forth. Hopefully that makes sense. All right. So now the next thing in terms of the laws of form is not just where do variables come from, but what can we do with variables? So one of the things that we can do with variables is that we can, once you have an algebra, you can introduce equations. So I have some expression E1 that I've generated from our grammar, and I have expression E2 that I've generated from our grammar. And I can form an equation. I can write down E1 equals E2. And what that implies is searching for a substitution for the variables that makes the statement true. It's a solution to the equation. Now, what's interesting to me in this approach, or in this way of thinking about things, is that is the question of who forms these equations. What agency is responsible for the formation of equations, right? And in classical mathematics, that question is left hanging in the air. It's out in the background, in the ether, right? Because mathematicians form these equations and then they look for solutions. But mathematicians, you know, in the classical time period weren't thinking about computers that had an agency that was in some respects like the mathematicians. And so they could form equations and they could, you know, automatically search for solutions, right? But this basic procedure has driven the development of a whole ton of classical mathematics. Some agent, like a mathematician, forms an equation and then you search for solutions. And this has driven, you know, like the development of number theory, analysis, abstract algebra, a whole bunch of different things, right? Galois theory, in some sense, is all about, you know, extension of groups in order to find solutions to equations, right? The famous problem of can you trisect an angle is solved using Galois theory, you know, extending groups in a particular way. So a lot of mathematics has been developed by this particular approach after you've introduced variables, is to introduce equations and then search for substitutions for those variables that make the equations true. Hopefully that's clear. Now in computing, there's a different thing that you can do with variables. Again, it's all about the creation of substitutions. But the substitutions, what we've done is we've moved the development of substitutions internal to the agency that's available within within the expressions, right? So we could clearly introduce, we could treat the laws of form expressions as built-in variables for a lambda calculus. And so therefore, we can easily build lambda calculi that have built-in values, right? So, lambda with true and false, or lambda with the natural numbers, these are all well understood, well studied objects. So extending it with the Spencer-Brown algebraic expressions is also something that is well known, and we know how to do it. Likewise, you can have the Spencer-Brown values built into the row calculus, right? And again, we know what that's like, right? Row-lang follows the lambda pattern by introducing built-in values as first-class citizens, so they are processes in the row calculus. So none of that is particularly new. The only thing is we're now importing a different domain of built-in entities. That's it. However, what we have done is shift our perspective, right? So the important thing is that we've moved the agency of the development of the substitutions into the expressions. The expressions are forming the substitutions, right? And that is a result of reduction. This is kind of an important thing. So I want people to understand this point. Do you see what I'm saying? When you reduce an application, or when you reduce a COM situation, when you run the COM rule, you are creating a substitution which you're then applying in subsequent expressions.
Are you changing the meaning of crossing and quelling?
Nope. Nope. They
If we have, X is distinct from Y, and X and Y are row-lang, what does that mean?
So again, the point is that variables can, if we go all the way back here, so when we're talking about X and Y, variables can come from anywhere. They can be strings or whatever you want them to be. They can also be quoted expressions, which would mean they would be quoted expressions of any form, right? But they still perform the function of standing in for something and therefore supporting substitution. And that's the important thing. And as for crossing, what crossing means is to be nested inside parens. That's all it means.
When you say create substitution, do you really mean to have some expressions with holes where?
No. It's actually the filling of the holes. What we're saying is that when we like, if I have an expression like this in parallel with an expression like this, we create the substitution that Y is bound to the quote of E. And then we apply that substitution throughout the body. Does that make sense?
And this is just like alpha equivalence, right?
No, that's not alpha equivalence. Alpha equivalence is I can change y in any way as long as I'm consistently changing it throughout the body, right? So it doesn't matter what I put here as long as I don't accidentally capture something here that wasn't captured before, right? So alpha equivalence is these variables are of a different, like it doesn't matter what the actual name of the variable is. It's sort of an abstract whole, but a substitution is taking the value and filling it in the whole.
I see. So oh yeah. This basically means that we are normalizing or reducing something, or
yes, right. So when you apply a lambda to a value, what you're doing is you create a substitution, which is x, it stands for the value, and then you apply that substitution throughout the body. Yeah, and go ahead.
Creating substitution is basically abstraction.
No, abstraction is making a hole in something and saying, I'm not going to evaluate this thing until you give me something.
Oh, so you said we are filling the hole. So we are basically doing application, like
Application creates a substitution. Yes.
Oh, okay.
And com creates a substitution.
Okay, understand.
Right. Okay. And but the important thing is to note that equations also create substitutions. Right. But the management of that substitution really has to do with like the agent that formed the equation. Who wrote down this equation, right? Well, in the case of Einstein's equations, Einstein wrote them down. In the case of Newton's equations, Newton wrote them down. That's why they're given names, right? Those equations are given names because there are certain agents, famous agents, who famously proposed these equations, right? So the agent is on the outside of the system, not on the inside of the system. That's the important point. There is a fundamental shift in classical mathematics from classical mathematics to computing, where agency moves from, some God's eye point of view, some uber entity that is on the outside of the system manipulating the system, to putting a lot of that agency inside the system. Does that make sense?
Yes.
Okay, that's very crucial, right? That's a cultural shift in thinking. It's fundamentally the shift from maths to computing. Okay, now one might logically ask, having observed this basic characteristic of equations versus reduction, we might ask, can I put those two ideas together? And to the best of my knowledge, I'm the only one that has asked this question. I could be wrong. There could be other people who have studied this, but I have done fairly exhaustive review of the literature. Then nobody has proposed this. The first time I proposed it was in a language called Highwire, which is a precursor to Rolang. If I were to reformulate those ideas in Rolang, it looks like this. So it's the same. It's the same grammar, but our com rule is different, right? And in particular, instead of having a variable here, I can have any expression. And the way we reduce is we form the equation. Oh, it looks like I got this wrong. Sorry, let me just quickly modify this. Hello. Oh, of course. There we go. this should be 2. Oops. Okay, there we go. Sorry. So what we're going to do is this thing, which is being output, is going to be formed into an equation with this thing. And when sigma is a solution, in other words, it provides a substitution that makes this equation true, then that substitution is applied to the body of the forward comprehension. So it's similar to pattern matching, right? The way we do pattern matching today in Rolang, but it is not the same. In particular, pattern matching will have a most general unifier. In other words, a unique solution. If these were quadratic equations, there might be 2 solutions that are not unique. Does that make sense?
Yes.
In which case, there's another source of non-determinism, right? That source of non-determinism is selecting a solution, right? So, for example, if you think about prologue can have different solutions because there are different substitutions that work to make your assertions true. And you can, there are rules like the cut rule in prologue, which allows you to manipulate the solution space. But in general, in this setting, and without going down that particular path, this gives you a source of non-determinism, because there might be an infinite number of these that allow for this. Now notice, for example, if E is a forward comprehension and this is a send, there is no solution, right? So if there's no solution, it doesn't reduce. You'll only have solutions when you have expressions with variables that you can actually find where you can find a substitution that makes the 2 sides of the equation the same.
So this means we are searching proofs. We are specifying the equation and we are searching for proofs.
No. You're only searching for substitutions.
And
You can generalize to proofs. You can generalize this situation to proofs, but it is not quite the same. It's similar to prologue, but it's not full-on prologue. Anyway, I think this is quite interesting. I think this is well worth exploring as a computational model, and look how easily it nests inside Rolang. And in general, so just one more point. If we are searching for, essentially what we want to do, and the reason I keep stressing design level thinking, this is another design level idea, right? The next generation of computer programmers have to be able to, on the fly, invent a language that suits the domain of the client they're trying to develop. This was the notion of domain-specific languages, right? Here, I'm presenting a way to refine Rolang to a slightly different language. It's actually not slightly different. It's actually quite different in terms of its semantics. But it's the delta from the design of Rolang to the design of this language is really quite small. We see how to do it. And so what we want to do is to reach out to the next generation of programmers who need to be able to work at that level. Design a language that meets the domain of your client. I am now sitting next to a bunch of biologists who are interested in biological processes that are implicated in cancer. I want to design a language that fits their domain. Right? I'm now sitting next to a bunch of geologists who are looking at the consequences of what has happened to a particular region as a result of fracking, and want to design a language that fits their domain. That's the idea. And so when I talk about design level thinking, I'm talking about being facile enough with things that make languages tick, that you can on the fly create a language that is best suited to the domain. That's the idea of domain specific languages. And it's a very good one, and it goes way, way back, right? So in the structure and interpretation of computer programs, that's essentially what they were proposing. That's way, way back to the beginnings of Scheme, right? So this is the computer science perspective. Now, it's all returning to the laws of form. One of the things that's most interesting is that Spencer Brown points out that once you can form equations, there are equations that do not have solutions in the two-value set. In particular, here's an equation that Spencer Brown points out does not have a solution. And in the mathematics of his time, he was looking for something like the extension of the reals and square root with imaginary. Right, so he wanted an imaginary value. Like for us, as soon as we see that it's S expressions, as computer scientists, we say, no problem. I know what a circular S expression looks like. Not a problem. Right? We can write that down. We're happy to write that down. Varela and Kaufman denote this value with the script O and propose a particular arithmetic. We can check whether or not that arithmetic makes sense in terms of circular lists. But they are able to show a form of completeness so Varela proposes three equivalences. One of his is that those three are shown to be insufficient. Kaufman proposes a replacement for one of them. So you get these three, and that turns out to be complete for a class of expressions, for a class of equations. Now, Sharp points out that it is not complete for general expressions of the form, give me an expression in X, F, an expression in XG, and then, form an equation. In particular, he points out that this equation does not have a solution in the Varela-Kaufman extension to the laws of form. I want to point out that we can provide a very wide variety of these laws of form. In particular, we can have different colored nested parens, and you can give different rules as to how nesting how you're allowed to go into a nested expression, right? So red nesting doesn't give you the access to black nesting, and black nesting doesn't give you access to red nesting, right? So I've given examples of red-black sets many times. So this is just an extension of that idea. Two colors is not, there's no requirement that you restrict yourself to two colors. And the graph that you build of how you can go from, one color to the next, right? So this is a little loop, right? You can, blacks are atoms for red and reds are atoms for black, but you could have, red, black, and yellow. And then you can get like a loop that goes that way, or you can build a different graph. So in general, you can build a little state machine for how the nesting works. So there's absolutely an infinite variety that we can use. And finally, if you interpret crossing in terms of the row calculus operations as not nesting in parens, but swapping polarities of input and output, then it is possible to construct an interpretation of Sharp's equation. So if this is an out, right? This is an out, that's an out, but the cross turns it to a 4. So now you have a 4, and you have to interpret multiplication for the concurrency part as a concurrent composition. Now you have the most basic 4 running against the most basic output, and that will result in 0. So there is at least, I mean, I haven't presented you any of the details, just given you a sketch of how to do it, because I'm hoping that these ideas make it, spark your imagination and let some of you or someone else who's listening to this later, take it further. Essentially what I've done is, shown, kind of taking the lid off of this thing. It's not very mysterious at all. We know how to model these, and there is quite but there's this wider universe into which it can be situated that makes it very interesting. So anyway, that's the basic elements of information. Any questions on the basis of this talk?
So when you say that we are designing a domain-specific language, in this way, we are not extending Roland with additional constructors, right? We are just changing the shape of like existing terms.
So no, there's a wide range of things that you can do, right? So in particular, we did change the constructor, right? Here, where there used to be a value, we're putting an expression.
I see.
So we changed this constructor.
I'm thinking what you said previously, that is not needed to add new constructors. We can just like make these kind of changes. Previously you said that this is like much more like easy way to extend the language than just add new constructors. So I'm thinking of that.
Sure. The main thing is that you're not bound into one way of thinking. You understand all the different ways that the system has give and play. And once you understand all the different ways that the system has give and play, then you can say, well, I can change this, or I can change that, or I can, right? When you change the COM rule, you're changing the basic engine of computation. Right.
And we can also add different COM rules.
You can add different COM rules, for example. Yeah. But the key point, like in all of these, so whether it's this calculus or the space-time calculus that I presented, or all of the calculi that I showed with the design level thinking course, and the design level thinking talk that I gave in January of 2019, all of those different constructions are about how to ring changes on these calculi, so that you have a feel for, okay, I can modify it this way, and that modification lines it up with the this particular aspect of a given domain. Like so this one might be good for number theorists, right? Who are interested in exploring solutions to certain equations, because this will generate. You can set this up to generate certain equational spaces to solve. Any other questions? Awesome. Well, thank you so much. I really appreciate it. I heartily recommend Spencer Brown's book, The Laws of Form. It's very entertaining. It's written in the mindset and language of the mathematics of the time, which has a particular flair and sensibility. That
I read it back in the 70s,
exactly.
and it changed my life.
Awesome. Fantastic. Yes. Yeah. So I recommend that other people take a look at it. And especially now that, I mean, the same thing happened to Lambda, right? Because people found the paradoxical combinator, people thought Lambda calculus was suspect. They thought maybe it was degenerate, that there were no non-trivial models. Right. So the laws of form's reputation, it has good bedfellows in the sense that people thought maybe it was nonsense, but when you spent a little bit more time with it, it turned out to have more substance to it. I also heartily recommend. I haven't read Varela and Kaufman's work, or I skimmed it a very long time ago. But I heartily recommend Sharp's paper. It's quite interesting because here's a classical trained mathematician, treating it with the rigor that comes from that era of mathematics. He wasn't a computer scientist, so he didn't have a lot of the tools, but he did have a very clear understanding of what it was to build a model, and what it means for a model to have good properties. So this is a very, very well-written paper in my estimation. So I would heartily recommend that, and also Sharp's other work as well. Yeah, so that's what I wanted to share. The reason I did this is because it was the holiday weekend, and I thought it's very useful just to have fun sometimes. All right. Unless there's any other questions or comments, we can close it up here.
Can I ask you something from the last session? Because yes. I was looking at this again, and last session was amazing, and probably for the next time I will like understand this one. You said you said that we can remove confluence, and I was thinking as now that like I'm better understanding. Is it make sense that having confluence means that we erased something? So it makes sense to say that we are not removing confluence, but we are not erasing something.
That's correct. That's So what confluence really does is it identifies certain things, right? That's really at least in classical logic, that's really what's happening, is that we're identifying proofs that somehow, if we want to preserve the computational content of classical proofs, we can't identify them.
It is somehow similar how we are syntactically erasing, for example, in raw calculus, nil par processes equal as the process itself.
It's not the same as that. It's more like
so this is on the reduction side, not on the structural side, right?
I mean, there isn't a reduction that gets rid of nil par, zero par p is not reduced. It's only structurally equated.
Mm-hmm. And the confluence is more about reduction, right?
Yes, confluence is about reduction, right? It's yeah. Yeah, I mean, pi calculus is not confluent because you clearly have race conditions.
I see.
Yeah. I also found, since you mentioned, I also found a gold mine. I found a paper that talks specifically about V extensions or V enrichments of Yoneda. and builds up the understanding from the core idea that we can extend the notion of power set on the basis of the relationship between the power set monad and the category of sets and relations. So it turns out that the category of sets and relations is the Kleisli. Well, there's an op in there, but I'm just going to ignore that. It's the Kleisli category, a category of algebras of the power set monad. And so it turns out that you can take this relationship of a power monad to its Kleisli and generate a very wide range of constructions that all are closely related to Uneta. In particular, you can show that the power set monad is recovered if what you're doing is you're mapping your set to a if you take the way you generate relations is X cross Y gets mapped to the gadget 2, right? 1 and 0. So it's the set containing 1 and 0. That forms a trivial quantole, not the trivial quantole, but a very small quantole, right? And so you're mapping X cross, so X cross Y is related if the map goes to 1, and they're unrelated if the map goes to 0. Now you can replace 2 with any quantole. And that tells you sort of the degree, it tells you the degree to which X cross Y are related, or the quality of the relationship. And once you do that, then the corresponding, so that gives you a power set like gadget, and it gives you a relation like gadget. And that's a clear, smooth transition from classical, models of classical logic to, or intuitionistic logic, to models of linear logic. Is this, you parameterize the power set construction in this way, right? So that you're looking at X cross Y to some quantole. And when you go X cross Y to 2, you recover the power set monad, the ordinary covariant power set monad, and the category of sets and relations. And when you generalize that power set monad to some by generalizing the quantole, so X cross Y goes to some quantole Q, then you get a new power set construction that gives you a sets and relations like thing that gives you models of linear logic. So that's how you smoothly transition. Essentially, a lot of the work that I've been doing is to try to find some kind of continuity, some continuous path from one logic to the other. How do I smoothly deform one logic to another, right? You can think of it that way, or you can think of it modularly. What are the modules that when I put them together give me classical logic, or I put them together slightly differently, I get linear logic, or when I put them slightly differently, I get modal logics, right? That's another way of thinking about, it's sort of the engineering toolkit for logics. That's another way of thinking about this whole idea. And this piece that I discovered is well known. It's nice because it fits into the construction that Christian has been investigating. So it's quite.
When you say,
go ahead.
Sorry. When you say that you have smooth transition, are you thinking about that in the same way how you said for geometry you can go between geometries? for example, can you go to
Yes.
classical logic, then go back, and then to different logic, and then to some another, and then you're mixing this together?
Yeah, that's the idea. It's design level thinking for logic, right? So I've been exposing some design level thinking for the design of computer programs, right? Computer programming languages. We want to be able to do the same thing for the logics, right? But we know that logics are not quite the same. It's a slightly different perspective. And what I've been essentially trying to provide is a homomorphic view or a microcosmic principle for programming and logic. So essentially what I'm trying to show is that the logical view is the same as the programming view, but at the level of the collection, right? So the programs are about the individuals, the logical expressions are about populations. And if you can bring about this idea, then you can use logic as the means to program self-organizing collections. That's the goal, right? Because as we start moving towards, genetic, biological programming, like DNA-based calculations and things like that, right? We explicit do this, then do that, then do this, do these two things in parallel. That kind of programming doesn't work, right? Declarative programming is a much better, can you please arrange yourselves, I don't care how, so that you can evince this property. That's the idea for population programming. I don't care how you get it done, right? This is the way you want to program organizations. I don't care how you get it done, but I need you to be able to convert this kind of input to that kind of output.
So we need to understand the properties that we want to just combine.
That's right. We understand the properties and the meaning of those properties are witnesses, of populations that can do this. That's the idea.
I wonder, did logic programming develop beyond Prolog? I mean, Prolog itself didn't have a whole lot of, it was reasonably deployed, but not completely. But is there any newer language?
There's Oz and there's Lolly. So Oz took Prolog in the concurrency direction. And it's still a fairly active research community. And Lolly basically made a linear logic based Prolog. And I don't know how active that work is anymore. So you can look at those two. What I want is a general architecture, not one language tied to one logical expression. I want a general architecture. All of the logic programming languages must look like this.
Right.
This means that basically we can use any language as part of our bigger program that we are combining with our logical.
Yes, that's the idea. You go from a programming language to a logical world. Yes.
And this logical world is basically based on collections, right?
Well, yeah. What you're doing is you're lifting the program constructions to constructions on collections, and then you have some other operations that are indigenous to the notion of collection that you've got. So that's the idea. Yeah. Coolio. Thank you very much. I'll see some of you in the dev stand-up.
Thanks.
All right. Thank you.
Ciao, ciao.
See you. Bye-bye.